Okay, first of all, I want to thank the organizers for the nice meeting, nice venue, and and also the Nano Center. I'm going to talk about the interface that we're studying. Most of the here is my pointer. Okay, so most of the work I'm going to show was done by Moshe Ben Shalom, who could not come because he has to fly today with his helicopter. And these are my students, and we have collaborations with Alex Kerning and Yossi Larea, and David Rachmilevich from Alex Palevsky's group, and Alex Palevsky himself. And this is Tel Aviv, if you don't know. So artificially structured heterostructures, and basically what we want to do is take one material, let's say, and add another material, and then miraculously something new appears in between, and we hope that this thing is interesting. I'm a vegetarian, but this could be interesting, I don't know. And we're studying oxide interfaces, and why? First of all, they grow nicely, and they can be grown epitaxially, which means that the lattice can be just continued from one layer to another. And oxides usually share the same sublattice constant, so one oxide can be grown on the other. And of course, we have many tools for growing and characterizing oxides because we used to study high TC cuprates, and we're still studying them, and many tools were developed because of that. And they are oxides themselves. And here is one example. This is just a theoretical example now. Let's say if you take one ferroelectric and antiferromagnetic material, which is called multiferroic, and you grow a ferromagnetic material on top, and then if you apply electric field, this is a multiferroic material, you can reverse the polarization of the antiferromagnetic system, and then via the exchange bias you can reverse the polarization of the ferromagnetic layer. And this can be done, for example, for writing memories with electric field, which is nice because electric field is more concentrated than magnetic field. Another example was done in Jerusalem and also in Brookhaven. So this is taking one material which is, let's say, it does not have a superconductivity because it's underdosed, does not have enough carriers, and another material which is not superconducting because it has too many carriers, and then at the interface you have a superconductivity with a nice critical temperature. And this is the system that we are studying. It was discovered in 2004 by Otomo and Harold Wang, now in Stanford. They realized that they have to buy him because he's good. And he was American initially, but then he moved to Japan, and then came back to Stanford. Basically, when you grow, what they found is when you grow lanthanum aluminate, few layers of lanthanum aluminate on top of strontium titanate, you can get insulator, which is not very interesting because both materials are insulators. If it's strontium oxide terminated. But if you take this STO with the titanium oxide termination and you deposit lanthanum aluminate on top, then you get a conducting interface and very high conductivity actually. Later it was found that there is a conductivity threshold, which means now you deposit layer by layer. So if you deposit one layer or two layers or three layers, this material, this interface is still insulating, but when you deposit 4 and more, it becomes conducting. And this is the number of charge carriers, so you cannot detect them. And then you have 2 10 to the 13 per square centimeter charges for 4 layers and above. And it was later found out that this thing is also superconducting with TC, which is about 300 or 200 millikelvin, So this is the transition, this is the magnetic field. And maybe it is also magnetic. So here you see some magnetic hysteresis effects and very large magnetoresistance. Okay, sorry. So we decided this is interesting enough to study. Before that, strontium titanate has a very large dielectric constant. It's about 24,000 at low temperatures. So basically you can apply small biases or relatively small biases from the bottom of the substrate, which is 0.5 millimeter thick, and get a significant change in the carrier concentration. So here what they did, they basically changed the gate bias and modified the number of carriers, and via that they changed the superconducting critical temperature. So here they can actually scan the entire phase diagram of the superconducting state. This is low temperatures, and also this is the resistance, which is becoming from a metallic-like behavior becomes insulating-like. So basically by gating you can scan the phase diagram. Okay, and this is the geometry. There is a bridge, and this is the STO, and there is a gate on the bottom. And this is rather thick, but the dielectric constant is huge. Okay, so the ground state basically can be tuned by gate voltage. Okay, now this is okay. One slide was vanished. So basically, what is the conductivity mechanism? There are a few suggestions. I will tell you because I lost the slide. The first possibility that there is a cationic mixing. Maybe it's not very interesting. There is lanthanum mixing with the strontium. The second possibility is oxygen vacancies. And basically, these two possibilities, they do exist, but probably they are not the main contributors, because if there are oxygen vacancies and cationic mixing, why conductivity vanishes at 4 unit cells and above, or appears at 4 unit cells and above. And the last nice thing that was done is rewritable electrical circuits. So basically you sit at this 3 unit cell, so your material is now insulating, and you come with an AFM tip, you bias it, let's say to 3 volts relative to the sample, and then you can write circuits with your AFM tip. So this line below the AFM becomes conducting, and you see that they measure the conductivity between, the conductivity between this pad and this pad as a function of this AFM distance from that pad. So they just approach with the AFM tip, and when they connect these two pads, conductivity appears. So basically, in this way, you can actually write a transistor or something. And you can also cut this. So now they move perpendicular to this line, and they cut it. So here, this is the cut line. It's about 3 nanometers, and conductivity vanishes as soon as they cut this line. So you can write and erase circuits with this thing. So you grow 3 layers, say, so you're just below the conductivity threshold, and then you move with your AFM tip. And this holds for some time. It is quite stable if you put it in a, let's say, nitrogen environment. Just the electric field is stayed there. They say that this is some kind of water absorption. Okay, this was the slide that I wanted to show you. Okay, so now what is the origin of the charge carriers? If you look at the strontium titanate, it is now Ti2 terminated, but this material is basically neutral. Also, this material is neutral, but it comprised of charged layers. So LAO is plus, ALO is minus, and then you have plus, minus, plus, minus. And when you grow this material on top of that, you have electric potential which is growing. So as you add more and more layers, your electric potential increases. So this results in a very large energy, and of course it's not stable. So if half electrons per unit cell moves from this point to that point, then this electrical potential catastrophe relaxes, and you have this picture. So now the electrical potential just oscillates, and the energy is not diverging. So this is a schematic picture of this polar catastrophe. So if you have this picture in mind, you can imagine the reason why electrons would move to the interface. And then more detailed calculations came. This is Pencheva and Pickett. This is DFT plus U. Of course, they knew about this conductivity threshold, and they found it in their calculations, or reproduced it in their calculations. So if you have 1, 2, 3, or 4 monolayers, you have a gap here, and as you grow 5 monolayers and more in your computer, the gap closes, and you have conductivity here. So here you have a density of states at the Fermi level, and you have conductance. And also a nice thing to note is there is a change in the lattice, and when you have this many layers. And this was also found in X-ray and stuff. So what I'm going to talk about, I'll show you some, what's the time? Okay, I'll show you that some anomalous magnetotransport. I'll show you that spin-orbit interaction is important in this material, and this is important if you're going to use it for, let's say, spintronic applications. You want to control the spins via applying some electric field. I'll show you some phase-coherent transport and Shubnikov-de-Haas oscillations. You don't know what Shubnikov-de-Haas, maybe, some of you. So this is like my peg misunderstanding. And then I'll show you that multiple bands can explain some of the data. Okay, so first we want to make samples. We make it by pulse laser deposition. This is the laser chamber. So laser comes from outside of this chamber. It's a UV laser, 248 nanometers, 10 nanoseconds pulse. And the laser hits a target. In our case, it's lanthanum aluminate. And this is not lanthanum aluminate because the plum is quite large here. And there is a heated substrate here, and material evaporates on this, on the substrate. While the material is growing, we monitor the growth with a reed. We look with the electrons. Electrons beam is coming in a grazing incidence, and you have a detector, and you can actually look at the electron diffraction. So this is the diffraction from the surface of the strontium titanate, and the amplitude of these points changes when you have a very flat layer. So here you can look at the growth process. So here you have 1 unit cell, 2, 3, 4, 5, 6, 7, and 8 unit cells. So whenever you complete a layer, you have a peak in your intensity. So here we know that we grew 8 unit cells, and then we went to the TEM, or Moshe Ben Shalom, went to the TEM, and there was a very good guy there, Chuck Waitai, who unfortunately left, and he knew how to prepare these samples. And then we can make a TEM picture of this, and we can see that this is 8 unit cells, and here we grew 20 unit cells, and it's 20 unit cells, and the structure is nice, and everything is nice. And then we went to measure this thing. So we cool it down. This is what we know to do. So this is at 2 Kelvin, and we apply the magnetic field perpendicular to the current and to the surface. So here the magnetic field is out of the plane, and you have very large positive magnetoresistance. While it's parallel to the plane, you have negative magnetoresistance. Okay, this is weird. So this may be usual orbital effect, but here omega c tau, which basically determines the size of the orbital effect, is approximately 1, so you expect large effect. But this is unexpected, so this may be related to some spin effect or spin scattering effect. And this spin effect vanishes at 30K. And this 30K is important temperature somehow. We don't fully understand that yet. Also, a nice thing to note is this anisotropy. This anisotropy is very strong. So when you rotate the field outside of the plane, so here phi 90 is a field parallel to the current, and then you take the field out of the plane, and this is what you do. You scan the angle. So here it's parallel. You have negative magnetoresistance, very large, and here it's perpendicular. You have positive, very large. But if you see, these are very spiky features, and the width here is very small. It's 3 degrees only. So it means that you apply very small perpendicular field while applying very large parallel field, and this effect is gone. We don't understand that. Superconductivity. As I told you, these samples are superconducting, and we measured the superconductivity, and we actually tuned it with gate voltage, like in the other picture that I showed you. So here you put, this is the gate voltage applied on the bottom of the substrate. So 50 volt, it's this guy. You have many carriers, and you decrease the number of carriers, and superconductivity increases. So here you have about 350 millikelvin. So basically, if we look at this phase diagram, right, so we are studying this region here. Okay, so you increase the number of carriers, TC decreases, and if you decrease the number of carriers, TC increases. Going back. Okay. So we want to see what happens to the magnetoresistance. So if you apply perpendicular magnetoresistance, this is large field, 20 millikelvin, which means it's not done in Tel Aviv University. It's in Tallahassee. But maybe next year, FOD. Okay, so this is the parallel magnetoresistance. You apply now the field parallel, and there are many features here. So here, this is superconductivity, and you kill superconductivity with parallel field, and then you have some plateau, and then negative magnetoresistance, and then another plateau. And you see this thing shifts towards the high fields as you change the number of charge carriers. So this is large number and small number of charge carriers. If you look at the superconductivity, you see that the magnetic field is very high, basically. What do I mean high? If you want superconductivity to exist, you have Cooper pairs. So Cooper pairs means that there is a spin down and spin up, K down, K plus, and K minus. And when you apply the field, you can basically align the Cooper pairs. But usually you don't break superconductivity with that, you just introduce vortices. But this thing is two-dimensional. So when you apply the field parallel to the plane, you basically align the Cooper pairs. So this is how you break superconductivity. But if you look at the energy scale here, it's very large. So this is 2 Tesla or something. And this is huge. And there is you can estimate what field would break superconductivity if you just compare the energy, the magnetic energy of the spin, and the gap, the superconducting gap, which is the pairing energy of the Cooper pair. So this is the pairing energy, and this is the magnetic energy, and this is the line that you have. But here we exceeded this line by about a factor of 4, which means that something else is binding these Cooper pairs, and this thing is probably the spin-orbit coupling. So here we try to estimate the spin-orbit coupling from the magnetotransport, and we identified this field as the field which is characterizing the spin-orbit coupling. And this resistance is coming from spin-orbit scattering. So if you believe that this difference is proportional to the scattering time, and this field is proportional to the scattering, to this spin-orbit energy, then these things should scale. So this is H star. It should be proportional to epsilon SO, and the difference in resistance should be proportional to 1 over tau. And let's see if it works, and it is working. So this is delta R, so these are the blue squares, and this is the H star. These are the black triangles. And this is another old theory which predicts TC. If you have TC and HC2, you can extract the tau SO. So all these things work pretty well. So we believe that this is a measurement of the spin-orbit coupling, the question is what kind of spin-orbit coupling is it? Is it Rashba type or some other type? But I'm not going to get into the details. Okay, another thing that was done by David Rachmilevich, Alex Palevsky's student, is phase coherent transport, which is the first phase coherent transport on this material. So if you make a mesoscopic sample, which means the dimension of the sample are small, you can see quantum interference effects. So let's say the electron has some trajectory between the impurities, and you have impurities in every sample. So it scatters off the impurities and it makes some trajectory. Now, if you change the impurity configuration, it will have a different trajectory, and you will see some kind of interference pattern depending on the trajectory of the electron. So if you have an ability to change, to move around the impurities, you can see some kind of oscillations of the interference patterns of the electrons, which is basically the conductance. Now, we cannot change the impurities, but we can change the magnetic field. And the magnetic field will just change the trajectory because it will make the trajectory curved. And if you apply magnetic field, you would expect some kind of reproducible interference pattern. Okay, and this is the measurement. So here you see this is the signature of spin orbit, and these are the interference patterns. So this is universal conductance fluctuations, and you see this thing is reproducible, and you can extract all sorts of sizes which are important. Basically, the most important length scale is the phase coherence length. So if you want to make a quantum computer or something, you need to know what size or on what length scale the electron retain their phase memory, and it's about 2,000 angstroms, and it can be modified, of course, and hopefully improved. Yeah, maybe I will not dwell on that. The last thing maybe will be this Shubnikov-de-Haas effect. So this is another important effect. It is very small here, yet it is conspicuous. So, and the field is 32 Tesla. So we needed even higher fields, and the temperature is helium-3, so it's about 400 millikelvin. And this is perpendicular field magnetoresistance. So basically what you do, now the electrons are moving around the Fermi surface. So this is a measurement of the size of the Fermi surface, if you want. And the size of the Fermi surface is proportional to the number of charge carriers. So you can extract the number of charge carriers and their mass from this measurement. So basically here you see nothing, but then we extracted a straight line from that, and then this thing is revealed. And when you subtract this polynomial, this green polynomial out of that, what do you see? Here is what you see. So these are the data. So this is at various temperatures and various gate voltages. So you change the number of charge carriers and this thing changes. And also you change the temperature and the amplitude changes. And from that we can extract the number of charge carriers or the area of the Fermi surface. And from this thing we can extract the effective mass and the scattering time or temperature. And the interesting thing is that if we look at the number of charge carriers extracted from this measurement, it is about 10 to the 12th carriers per square centimeter, while from the whole you get 10 to the 13. So what we can do, we can assume that there are multiple bands and maybe degeneracy. So each band has, let's say, spin degeneracy, spin up and spin down, and maybe other degeneracies. And we look at the whole. This is the whole measurement. You know what whole measurement is? Maybe. You apply a... yeah, you know it. Okay. Okay, so basically you measure the transverse voltage when you apply magnetic field. And this is proportional to the inverse of the carrier concentration. So the slope here is 1 over n. But you see there are two slopes here. So we look at the two-band contribution. If you have two bands, you have a b squared term here in rho xy, if you divided out the b. So we fit, the fits are very nice, and I think we were able to reconcile all this stuff, the Hall and the Shubnikov, assuming that there are multiple bands, and there is degeneracy, which I'm not going to talk about, which is of the order of 6 or maybe 8, because 2 of the spin and another 4 or 3 coming from other places. We measured the Nernst effect, and that's the summary. This is a very interesting system. There is strong spin orbit, which means that it may be applicable in 20 years or so. There is a phase coherence length, which is reasonable. Maybe we can improve it, and we measure some properties, coherent transport, and these are all the people participated, and you can read the papers if you're interested, and thank you very much.
You have superconductivity, you have spin-orbit coupling, you have, I think, every effect I've ever heard of in solid-state physics. What makes this material so unique that you have all these things, or is it...
The question is whether superconductivity and magnetism coexist, and if this is really magnetism, I'm not sure. Spin-orbit coupling and superconductivity, they can live together. The main question maybe now is whether it's magnetic and superconducting. But maybe these are other regions in the phase diagram. So you have a magnetic region and superconducting region, and you can tune through them using this number of charge carriers. So if you change the number of charge carriers, you can be sometimes superconducting, sometimes magnetic, and maybe both. I don't know.
And so the way you change it is just this thickness that you have in the interface, or?
No, we change it through the applying gate voltage. Mm-hmm. So the gate voltage determines the number of charge carriers. It's like a capacitor. So some kind of a capacitor. So if you change the voltage, you change the number of carriers in each plate. So also the thickness has an effect, but basically it's a 2D system. So the LAO layer doesn't play a major role. It's just the interface between this lanthanum aluminate and the strontium titanate. This is the conducting layer, and superconducting.
And magnetic.
And magnetic, maybe.
Okay.
When this layer is in the superconducting state, and you take it out of the superconducting state or back in by changing the gate voltage, do you know how fast the transition is?
As a function of magnetic field?
No. Not magnetic field. Electric field. You apply a gate voltage and you can change it because you change the superconducting
I see
temperature, so you can change it from normal to superconducting. How fast is this, do you know?
I don't know, no. Because usually we do it quite slowly, so probably we cannot do it that fast.
There might be some applications if you can do it fast enough.
Yeah, but these are large voltages that you have to apply. If you want to take it out of the superconducting region, you have to apply 100 volts or something.
Even if you're very close to DC?
Yeah, maybe if you're very close, but then you have to be at I see what you're saying. Yeah, very close to DC and then move away. But you have to be at 300 millikelvin. Yeah.
Okay, any questions? And let's thank all the speakers of the session.